So I signed up to talk about deveining, though I am by no means, any means whatsoever, an expert on this. So I borrowed 90% of this directly from Layer fMRI. There is a lovely, Renzo's put a lovely explanation, tutorial, figure extravaganza on deveining and removing the bias of gradient echo bold, the veinous bias. He also has the test data as part of the Laney suite. The other 10% probably just comes directly from Kendrick K's paper. So anything good about this is theirs. Any mistakes are pretty much my own. Renzo, if I say anything too incorrect, just wave your hands because I can see you, and I'll let you clarify it. But generally, there's something in if you collected gradient of echo bold data, and you might think it looks great, but there's something wrong with it. But at first approximation, the response when people see gradient echo bold, particularly when they compare it to spin echo or vaso, is it just looks great. Over here on the left, we have the vaso signal, and it's sickly, it's weak. There's only a little bit of activity. And the gradient echo bold is huge. You have this massive signal. Look at all these areas. Look at all these blobs. It kind of looks fantastic. And you're like, okay, this is a finger tapping task. So that's the finger spot. We're pretty much done. But if you actually look at your data, which is probably the most important thing, you start to realize there's an issue here. Renzo's talked about this extensively. It's not only is it biased towards the superficial layers, it's biased in that it's outside of kind of the gray matter you care about. It's practically out in what appears to be CSF. And that's just because of the properties of gradient echo bold. So it's not great, it's a problem. So the problem is that you have little events, maybe activity A and activity B happening somewhere in the vascular tree, but what you kind of see those. It's not that they disappear. So it's not that gradient echo bold fails to capture those events. It's that your attention is instead attracted to this massive signal that appears at the superficial layer where the veins are largest, and out beyond that. So you have this kind of nonsensical signal that is displaced maybe even up to 4 millimeters away from where you thought your activity should be. Now, I will say that this is only a problem if you really care about precision. So obviously in a layer fMRI sense, anything where you're trying to determine things by depth, that obviously matters. And if you have this precision where 4 millimeters is many voxels, then yes, this is absolutely a problem. But for many people, they really don't care about this, and they're kind of happy about it. But I do think we care. So the goal is to how do we get rid of this weird bias towards the superficial layers that doesn't really reflect the activity where it's happening. So Renzo's blog presents 3 ways of dealing with this, or 3 ideas with kind of approaches for them. And I'll talk about another one developed by Kendrick K. So the first one is what Renzo calls the offset model. And it's just, I like this one because it's very simple. And it kind of looks like the data to me. So if we look at the left panel, we have this linear offset. Note that these axes are reversed from the graphs that Renzo helped us produce a few weeks ago. So CSF is on the left. And what we're imagining is, let's see, if I can get a little laser pointer. So this is our true response. These are the double peaks that we've seen a couple times now. And what we've kind of have happen is these get added together. And so this is what we see. We see this superficial bias where even though it should be a small amount of signal out here at the border, small amount of neural activity at least, large amount of signal in gradient echo bold, it's still massively biased towards the surface levels, even though the information is there. And so the solution is, well, if you think it's a linear offset, just subtract it out of your data. This one's also the easiest to do in the Laney LND vein. All you need to do is provide it with the layers and the bold statistical map, or the bold activation map, something that shows the amplitude of values here. Let's see, okay. And once you provided this to Laney, it will will attempt to remove this offset. And so we're seeing that here. This area that used to be have inflated values is reduced. It's moved towards the activity. Peak of the activity is moved towards the more middle layers. I still wouldn't say it looks too much like the VASO data. So you can't get to this necessarily from the bold data, but perhaps you can reduce the bias. Of course, this is a very simple model. Perhaps there is a better way. The scaling model refers more to the idea that it's not just a simple it's not a linear increase. Nothing is quite that simple. But instead, there's some gain towards the CSF because of increased venous cerebral blood flow or blood volume. So there's more blood volume, venous blood volume towards the CSF. So there's more signal there compared to deeper in the gray matter. So we take our kind of classic double peak, and we're just magnifying certain parts of it to explain what we're seeing. To me, this one, at least with the toy data, this one doesn't look as much like the toy data, but it does make a lot of sense to me, but it's a little more complicated. Or at least when I was reading about it, I thought I was going to have to collect more data. There was something additional I had to do, but if you read that blog post, you'll understand it's not too bad. So we got 4 things to provide Delaney in this case. The layers in the original bold data, we've already had those. The columns can apparently be very easily generated from your layer data, just using Laney. But there's this new cerebral blood volume or venous cerebral blood volume that we have to provide. And this threw me for a minute because I've never collected any data that looks like this. The amplitude of low frequency fluctuations, the ALF, that is provided in the text suite looks like this. But I'm not sure how this image was produced, but there's a nice explanation. You can kind of estimate this sort of thing if you, or at least the script provided, if you just take the power spectrum of your data, take the mean of the power spectrum and scale it. And what you get when you do that, let's see if I can move my face. No, it's just going to be there. What you get is something that does look very similar to the data that's provided. I didn't get a chance to test this and see how it performed. It is a little noisier than the example provided, but I'm sure there's a good reason for that. It was very easy to create, and it came directly from the bold time series itself. So just the power spectrum, the mean of that power spectrum, and then per the script, I scaled it down. So this gives you some estimate of the blood volume that then Laney uses along a column to try and figure out what that gain was and correct it. So what you get here is something that looks, let's say, plausibly closer to the VASO data. One thing that I think it is important to point out is that it does look like it's a little noisier. It's a little more speckly, and that's because we've scaled it in some way using this estimate of the venous cerebral blood volume. So it does, I think the word is inherit, a little bit of noise from that estimate, but it does seem to look a little closer to the VASO data. So maybe it works a little better. The third leakage model is, I think, it's substantially more complicated, but it's still fairly easy to wrap your head around, I think, at least visually. So instead of imagining that it's just blood volume, we're thinking that, yes, there's some veins, they're taking the blood away, and they're taking the blood from somewhere that had signal, or has signal that's captured by gradient echo, and it's moving along that vascular tree. And as it moves, it gathers with other blood that had signal, and so you have this accumulation that's both blood volume and the signal traveling over space that is leading to some of the signal in lower layers are propagating up, and then that accumulated signal is propagating up. So you see something that looks very similar to a linear scaling model, but the physiology underneath it is much more complicated. Despite this complication, Laney requires no other information than what we've already made for the previous model, and attempts to deconvolve this effect over space. Again, this looks just naively, this looks like the scaling model that we looked at previously, and I've kept I kept Renzo's text in here because, again, the noise is an important detail here. I think these all make a lot of sense. These all deal with your data as in a sense of space. So you've collected all your data, you ran all your models, and you look at it, and you're like, yes, that's ugly. I wish I had used Vaso, but what can I do about it? But there is another way of dealing with this that, in the similar way that this is a deconvolution over space, you can think about a deconvolution over time. This was a method developed recently by Kendrick K here at CMRR in Minnesota. And the idea is rather than you done all this work to create a map and modify that, what if you modified your GLM instead? And he calls this TDM, or temporal deconvolution through manifold fitting. I'll talk about what that means in a moment with some very busy figures. The key idea is that those PO responses, those responses up towards the CSF, it's a subtle effect. It seems to be very consistent. So depth 1 here refers to surface, so it's near the CSF, and depth 6, dark blue, refers to near the white matter. And it's difficult to see here, but this blue peak is slightly to the left of this orange peak. So it's a little earlier, deeper in the vascular tree, deeper in the gray matter. Now, this looks kind of like the amplitude effect in the sense that those CSF layers, this is kind of the linear offset model to visualize. The higher layers have a larger amplitude effect than the deeper layers. And it's not of the same magnitude, but time to peak is consistently across all subjects. It's a little later at the surface versus the deep levels. So there's something there that we want to see if we can perhaps extract and use to our advantage. This is the figure that attempts to explain all of manifold fitting method in one shot. I'll try and walk you through it because it's very busy, but I think in the end it starts to make a lot of sense. It does require that you fit, so you pre-process your data. You're running some finite impulse response model first. You're trying to estimate what's the bold response to each condition over time. Not do a fit, but estimate the actual shape of that bold response. I think this could be a difficult step in some data, potentially due to noise levels or due to how the model was designed. So it has to be considered that I think everything is kind of adaptable to this approach, but it may require a little more work. You take these estimates and you take the first 3 PCs, and you might have to do some selection to get voxels that have reasonable responses. But these first 3 principal components of your FIR responses the first one looks kind of like an HRF, and the other 2 are just modulations of that HRF. He then projects this into a 3-dimensional sphere, which I will kind of gloss over that part. And we just kind of look down the top of the sphere, and what we see is, you can imagine this blob is a distribution of different mixtures of these 3 components. And you notice it kind of has a nice 2-dimensional Gaussian shape. So all Kendrick does is fit a 2D Gauss into that. One standard deviation along that, the major axis, gives you early time course responses. So these are ones that loaded very heavily on, or a little bit in certain positions along PCs 1, 2, and 3. And then on the other side of this axis, we have these late time courses. These are then just these two spots are then used to reconstruct a GLM that has, so this is an early response. If you're thinking about this as a design matrix, we have time by conditions. So these are the early responses for each conditions, and these are the late. You'll note that these are very overlapping, and in a GLM, GLMs aren't necessarily happy about that. So statistically, you're losing a little bit of sensitivity here because you have they're not collinear, but very close to collinear regressors. But you have this simple idea that the early responses should be deeper in the gray matter, and the late responses should reflect that venous contribution. They should be larger, and they should be, we're saying we think they're a little bit later. When you do this across multiple subjects, you find these nicely separate. They're very close together, but the early response has an earlier onset time, which reflects some people look at the early response of the bold signal as the more neurovascular specific, or neuronal specific, and that's kind of reflected here, and then it has an earlier response. But they're certainly different. What was funny to me is that this late response tracks almost perfectly to the default HRF provided by SPM. So it may be that our canonical model, and these are also visual cortex responses, which has a very classical response. So maybe it's that the canonical model that everyone has used has always been somewhat biased towards venous data. This is just fun to think about. How does it work? Kendrick is a big fan of making gigantic, massive figures. I think I could do an 8-minute presentation just on this alone. So let me orient you very quickly. Only have like one more slide. So we're looking at depth 1, the surface, depth 6, deeper in the cortex. This is just percent bold. If you look at the standard, just the first column, this reflects what the data I started with shows you. You have these large responses, so higher percent, up to 16 or more percent at the top depth, that decrease over time. There's our linear offset. When you separate out the early and late components, the fits change in that the early component now looks much flatter. Just if you say squint and blur your eyes, this is kind of a flat line. The late component retains this linear offset and perhaps even magnifies it. These are even higher values, and it's even perhaps lower at depth. If you look at some of the spots where it's the brightest, so the largest percent signal change, you'll note that these are dark areas in the EPI. Dark areas at this resolution are pretty much veins, and you can even see some maybe penetrating veins that still get captured by the late model. I'm not going to talk too much about the eccentricity. I haven't done too much with this, but one thing I will point out here is that the standard model looks very, very nice. You have these lovely eccentricity maps, and the early and late components, which have divided that in some way, they're a little, the early component, which we really care about, is a little uglier in some sense. So it's not going to be as clean because we're trying to fit both of these very close together regressors. However, we think that it's worked. If we just look at the specific stimulus, we can see that what really stands out to me is we have this nice structure in the early component that's relatively flat across depths, or relatively consistent across depths, whereas the late component really does seem to be capturing these large, oversized responses that we would associate with the venous signal. The paper is on bioRxiv. I think I linked it earlier, but if you just TDM Kindred K, there's far more example figures and supplemental figures that go into it. So we've seen space and time methods, but I'm still somewhat confused about some of these things. So some of the things I'm confused about are that the blog post mentions that you can use the temporal smoothing method to generate some ALF estimate. I was just wondering if there's any guidelines or recommendations for doing that. I fiddle with a little bit of smoothing and then taking some sort of standard deviation, but I'm very unfamiliar with how to generate that. However, it did still look kind of like the ALF image that was provided. Another question that comes to mind is, since I was using all this test data, if I'm doing deveining, should my layers there be equivalent to the layers I'm using for analysis? If I'm saying I'm trying to remove this bias, should those match? This is kind of related to a post you've already made in that should layers be equivalent to the number of voxels in a column, in which the suggestion is maybe not. One thing that I'm going to hopefully try and find out is, do these time and space methods give similar results? Obviously, Kendrick's images are wildly different from the voxel maps that we were looking at with Renzo's data. So it'd be nice to see if compare one to another, do they start to match? Visually, it looks like they are capturing very similar things, even though they're done across different dimensions. But we don't know yet. And then the final thing I'm thinking about is if there's a danger or some sort of miss in this voxel-wise layer approach, because I'm imagining that there is some way the slice can be oriented, and that the gray matter, the vein is perpendicular, or the vein is perfectly in plane with our slice. So we know that we've captured the direction of the vein perfectly. But if we imagine that we're very oblique through the gray matter, then perhaps we're not. Then perhaps all these models are not working, because we're saying within this column, we expect this is where the blood is traveling. But if our column is much too long or oblique in respect to the orientation of the cortex, perhaps there's some danger there. But I don't know. I haven't thought about that enough. And I was only working with 2D instantiations of this rather than using anything 3D.
Thank you, Logan.
Thank you.
Thanks.